Hi, I'm Andre from the High Performance Academy and welcome to this webinar. In this webinar we're going to be looking at tuning the acceleration enrichment on the AEM Infinity platform. Now, for anyone who has tuned an engine before, quite often you'll find that getting the acceleration enrichment part of the tune correct is actually quite challenging. It's one of those areas that I know a lot of tuners really struggle with, and it can have a really big impact on particularly how smoothly a car or the engine will perform, as well as how smoothly it will respond to throttle application by the driver. So it can actually have a really big impact on the overall sort of driving experience if the acceleration enrichment is set up correctly. Now, while we will be looking at in this webinar at tuning the acceleration enrichment on the AEM Infinity platform, you're going to find that a lot of the concepts that we will talk about are applicable to a wide range of engine management systems. Now, obviously, every engine management system has its own specific ways of doing this, but the general principle of what we're actually trying to achieve is fairly universal. If you are interested, we do already have another webinar in our archive looking at exactly the same functionality on the Link G4 and VIPEC series of ECUs. Okay, we'll start with why we actually need acceleration enrichment, and there's probably a misconception as to why we need acceleration enrichment in the first place. Now, this is probably borne out by the reason that a lot of the the reason this is borne out is probably because a lot of the ECUs on the market schedule their acceleration enrichment based on throttle position, or more correctly, the rate of change of throttle position. So how aggressively the driver is opening or closing the throttle. So you would tend to think it would be a reasonable connection to think that your requirement for acceleration enrichment is purely based on how quickly the driver is opening the throttle. It's actually not the throttle specifically that affects our acceleration enrichment requirements. Really, it's what that rapid throttle opening results inside the intake manifold and inside the engine. So I've got a diagram here. Now, I'll credit Motec for this. This is the best diagram I've found in describing what's actually going on, and this is just stolen blatantly from Motec's M1 help file to do with their fuel film modelling. So this unfortunately relatively low resolution photo that I've got here, picture that I've got here, shows you the intake port. So here we've got our intake valve and we've got our airflow coming down in towards the cylinder here. Okay, so what most people don't appreciate is that not all of the fuel that the injector is injecting into our engine goes straight into the combustion chamber. What we end up with is some amount of fuel wetting out the port wall, and that's being described by what's labelled here as fuel film. So some amount of the atomized fuel that's being sprayed out of our injector is going to end up wetting out, condensing on the wall of our intake port and forming a fuel film, or a puddle of fuel that sits there on the port wall. Now, the size of that puddle is dependent, or how much mass of fuel, I should say, that sits on that port wall is going to be dependent on a number of things. We've got airspeed, how quickly the air is going past the injector, also the angle and fitment of the injector, so whereabouts the injector is physically spraying. One of the really big effects is our pressure, which you can see is labelled here, the pressure in the port. At the same time, the other aspects that are important to consider are our spray pattern, the distance between the injector and the port wall, how much volume of fuel is being injected, and also aspects that will affect it are the temperature of the port wall and the temperature of the valve. So there's a number of factors, and it is really quite complex to model this correctly. So what happens in essence is the size of the fuel film, or the puddle of fuel on the port wall, is going to be constantly varying dependent on all of these parameters. Now, the effect of this is in steady state. So let's say we've got our engine up to operating temperature. We're sitting at 3000 RPM at 20% throttle. and we're in steady state conditions. So at that point, what we can see here on our diagram is that the fuel is vaporizing back off that port wall. So obviously, if this puddle didn't vaporize and make its way into the cylinder, the size of that puddle would just constantly be increasing, and that's obviously not very sensible. So we get two aspects of how this fuel makes it into the engine. First of all, we have the fuel vapor. So the fuel puddle is vaporizing back off the port wall. That's obviously helped as well when the port temperature increases. And we also have sort of droplets or puddles of liquid fuel also entering the cylinder as well. So that's the two ways the fuel is making it out of that puddle. So under steady state conditions, the fuel is evaporating off the port wall and making its way into the cylinder at the same rate it's being topped up by the injector. So we reach an equilibrium of a certain mass of fuel that's sitting on that port wall. However, one of the main factors that's going to affect the size of our puddle is our pressure in the intake port. And that pressure in the intake port is going to be drastically affected by our throttle opening. So when we're at very, very light throttle, we're going to have, so let's say idle or cruise, we're going to have high manifold vacuum. So there's a high manifold vacuum, and that affects the size of our fuel puddle. Generally what that's going to result in is a larger puddle of fuel on the port wall. And then if we go to wide open throttle, our manifold vacuum is decreased. We're operating hopefully pretty close to atmospheric pressure, and that changes the size of the fuel puddle. Now the problem with this is, as we change the size of the fuel puddle, there's a time lapse where the injected fuel that's coming out of the fuel injector is actually being used to top up the puddle on the port wall rather than making its way into the engine. So for instance, when we go from closed throttle and we mash the throttle straight to the floor, what's going to happen is we've gone from, I actually hit it around the wrong way, so I'll clear this up. We start with a small small fuel film at very low manifold pressure, so at idle and cruise. And if we go to wide open throttle, that puddle size increases. So what happens is when we mash the throttle straight to the floor, instead of the fuel coming out of the injector and going straight into the cylinder, a certain portion of that fuel is used to actually build up the size of that puddle until we reach equilibrium again. So during this period, we have this transient period where the fuel that the injector is supplying is not actually making it directly into the combustion chamber. Instead, it's being used to affect or top up the size of that puddle. And during this period, the engine will run lean. So this is why we need additional fuel to be supplied when we accelerate quickly. And conversely though, when we're at high throttle openings and we have atmospheric pressure in our intake port and then we close the throttle, exactly the opposite thing happens. Now we've got a large puddle of fuel on the port wall, and when we close our throttle, what happens is the fuel from the puddle will start evaporating off, and we've still got the fuel being supplied by our injector. So the puddle size is decreasing, and the extra fuel from that fuel puddle, the fuel film, is being ingested into the cylinder, so we momentarily run rich. So that's actually what's happening. It's not really the throttle position that's the important factor. It's the manifold pressure, or the intake manifold pressure at the point where the injector is spraying the fuel into the port. That's the important part. But when we change our throttle position, this affects the manifold pressure. Okay, so now we've got an understanding of what's actually going on inside the intake manifold and why we need that acceleration enrichment. Let's have a look at our AEM Infinity. I'm just going to talk you through the functionality we have available in the AEM Infinity. Now, before I do that though, one thing that's really critical, and this is an area that so many people come unstuck, this is probably without doubt the most common problem I see, is the VE, or the fuel table, hasn't been tuned correctly to start with. So if we've got an area of our fuel table, our volumetric efficiency table, that is, for example, too rich or too lean, and we're transitioning through that on a transient throttle, that's going to affect the fueling of the engine, understandably. And then if we're trying to account for that error in the VE table with our acceleration enrichment tuning, we're going to be chasing our tail. It's going to be all but impossible to do a really accurate job of tuning the acceleration enrichment, and one way or another we're going to end up with a bit of a mess on our hands. So if you've gone through either our practical road tuning or practical dyno tuning course, you'll know that the first step in this whole process, even before we consider acceleration enrichment, is to make sure that our VE table or our fuel table is properly tuned to start with. We really want to see this accurately tuned, and I'd like to see no more than a few percent variation in that table. Now, this particular car doesn't ever really get the opportunity, sadly, to be correctly tuned. It's always being swapped between different ECUs, and we're using it for one particular job at a time. So this is actually a pretty poor example, and I know for a fact that this VE table still needs some work. However, what I've done before this webinar is just made sure that in the points I'm going to be looking at, we're close enough to get a general idea of what's going on. So that's our first place to start. And if we move across to our fuel trims tab, this has got the correction area for our acceleration enrichment. And in AEM speak, the acceleration enrichment is dealt with these two wall wetting sheets or worksheets here, or tables I should say. So to adjust these tables and make them work how you'd like them to work, we've also got some adjustability available through our setup wizard. And what we need to do, I've already got this open, but if you open the setup wizard for a start, you're only going to have access to the basic setup, and we need to click on the little advanced setup drop down tab and allow us access to the rest of these functions. So the worksheet that we want to be looking at in the setup wizard is our accel and decel fuel. Now, for a start, we only have access to our wall wetting 1 worksheet, and we can choose both the x-axis and the y-axis setup. Now, remember I said that it's really the manifold pressure that is the critical element to what's going on with our wall wetting and the size of that fuel film. And I've already said that by far the majority of aftermarket ECU manufacturers kind of work this in a roundabout way, because they link the manifold pressure change to change in throttle position. Now, technically it's not really the correct way of doing it, because it's that manifold pressure change we're looking at, but there are a variety of reasons why often using throttle position is actually an easier technique and is going to make our job easier as a tuner. One of the reasons is to do it properly from manifold pressure alone, we need to have the manifold pressure sensor fitted in such a way that it's going to get very, very fast response. The other thing is we get into an area where the response of the manifold pressure sensor can become problematic. If it's fast enough to give us really good response for our fuel film modeling, it can end up causing problems with the actual drivability of the car. So with the AEM, we do have the ability to use manifold pressure change rate, or we can use manifold pressure as a raw input, or we can use throttle position. I'm going to leave it on throttle position because I honestly feel that despite it being a bit of a workaround, in 99% of cases this is the easiest way of approaching it. The other thing is the fuel film model that I just took you through, the little diagram that I just took you through and explained, I feel that's important to understand what's really going on in the background. However, for most people, it's easier to link mentally the idea of opening the throttle sharply with requiring more fuel. It just seems to make more sense. So I'm going to leave the x-axis set up to throttle rate, and the other thing I'm going to do is leave the y-axis set up to engine speed. Now, if we just pop back to our diagram here, you can see that one of the parameters that I've listed, Motec actually have listed here as a effect on the fuel film size is our airspeed, or airspeed and mass. Okay, so what that means is we will probably want to change the amount of acceleration enrichment being provided based on the engine RPM. So at very, very high engine speeds, we've got very high airflow through the ports as well. And what we find is that we don't have so much fuel film on the port wall. It's just basically being stripped off by that airspeed, and hence we don't need anywhere near as much acceleration enrichment at very high engine RPM. So that's what we're going to be able to do by adding in a y-axis there. We're going to be able to affect the amount of acceleration enrichment being provided based on both the rate of change of throttle position and the engine RPM. Okay, so if we click on the Show Advanced setup, the other thing we can do is set up our wall wetting 2 table. Now this is an additive table, and again I'm going to leave the corrections set at the defaults that AEM have suggested, in which case on this second table our x-axis is throttle rate and our y-axis this time is coolant temperature. Okay, so let's just go back again to our diagram. Now again, you can see one of the parameters that is affecting our fuel film size is our wall temperature or port temperature. That's affected by the engine's coolant temperature. So what we find is that when the port is very, very cold, so when we first start our engine when it's cold, the port is cold, and that allows the fuel film to become larger. So we have a larger fuel film active, and that's going to have a larger effect on our need for acceleration enrichment. In essence, when the engine is cold, we need to provide slightly more acceleration enrichment. So we can do that through our second table, and we'll just go back and have a look at that now. So once we've got those set up, as I say, I've simply left those at our default values, and this is the default tables as provided by AEM in the Infinity. So we've got our wall wetting 1 and our wall wetting 2. Now the wall wetting 2 at the moment you can see is filled with zeros, and I'm going to talk about how we will deal with tuning that shortly, but we would start always with our primary wall wetting, and we're going to start with that with our VE table properly tuned and our engine at operating temperature. Now I'm going to just use the PC logging function of the Infinity here to help show what's going on, and let's start by just simply highlighting the entire table there and setting it all to 0. Okay, so it's always the easiest place to start, and let's have a look at what happens when we've got no acceleration enrichment active at all. Okay, so I've just given the engine a really sharp rev, and I'm going to do that again, and we'll just stop the data logger and I'll have a look at what's been going on. Okay, so we'll stop that log so we can actually view it and have a look through it, and this will make a little bit more apparent what is actually happening when we open our throttle very, very quickly. So again, remember at this point we've got absolutely no enrichment happening at all. So this yellow trace here is our throttle opening, and you can see that we started down here with the throttle closed, and you can see the line here as I've opened the throttle very sharply. The green line here is our lambda, and you can see that we start back here at idle with a normal 14.7 to 1 lambda 1, and you can see that it's actually jumped very, very lean. In this case we're using AFR units. This is registering 26.5 to 1 at the point that I've got the cursor, so it's not ideal. At this point here, we've overcome that lack of fuel film. That fuel film has been built up, and we've reached equilibrium again, and then we've actually dropped to our target lambda, or close to, in which case we're now at about 13.8. So actually our target was 13.0, but under a transient condition like that, it's unlikely we're going to see a really good sort of example of us reaching our target. Okay, so that's what we get when we've got absolutely no acceleration enrichment. At the other end of the scale though, if we just bring this across a little bit, You can also see in this area here where I back off the throttle, you can see that our lambda or air fuel ratio drops quite rich, so we go into a bit of a trough. So this is pretty typical of what we'd expect to see with no acceleration enrichment set up at all. Now the problem with this is it's going to almost certainly make the engine feel hesitant under sharp acceleration. Chances are, unless it's excessive, the overly rich area when we decelerate probably isn't going to be that noticeable, but we can still correct it to a degree, so we will look at that later. But it's the sharp acceleration that is the part that we really notice. Okay, so let's simply add some fuel into our wall wetting 1 table, and we'll see how that affects the shape of this big lean area that we're really not that happy with and we want to get rid of. Before we do that though, it's always useful to see whereabouts in the tables we're actually accessing. So what particular part of the table we're actually accessing, and as we move through the log file, you can see that the ECU shows us the areas in the tables that were being accessed at that particular point. So you can see here this cell highlighted here in purple is the current cell at this point in the log file that the ECU is accessing. That's really important to use the data logging to help you tune your acceleration enrichment. Without that, you're really going to struggle because you're going to be guessing to a degree on whereabouts in the tables the ECU is accessing. So what I've actually done as well is I've added a couple of one parameter onto this log file. I've added, you might not be able to see it too easily because it's in black, I've added throttle rate, so the change of throttle, the rate at which the throttle is being changed, and that is the same as the parameter we have up here. So I can just see exactly what that throttle rate is, and you can see here if I look at the area in the table, in the graph where I first went to full throttle, you can see that we've jumped up to around about this 800% mark, but more accurately we can actually see exactly what we were getting in the log file by adding that parameter. And if you want to know how you can do that, you can right click on the plot and you can click on set channels, and that'll show you a full list of all the channels and you can choose them. So in this case I chose throttle rate, which is available there. You can see that it's already been added in. Okay, so let's get our log file running again, and now what we're going to do is we're going to add a little bit of fuel in the areas that we were running through in our log file. Now what you can see I've just done here is I've increased the fueling around this throttle rate of 400. I've increased the fuel by 5%. Then at 800 we've gone up to 10%, and then at 1000 we've gone up to 20%. Now that's simply because the sharper we open the throttle, the more that manifold pressure at the injector is going to change, and that's going to have a larger impact on the size of our fuel film or our fuel puddle on the port wall, and hence the more sharply and quickly we change our throttle position, the more additional fueling we need to add. Alright, so let's now give our new numbers a bit of a test. And I'll just do another test there. Okay, so let's just stop that log file and we'll have a quick look at that. And again, I don't really care about saving this at the moment, so we'll just zoom in a little bit. Yeah, probably our first test was a better one. And remember, in our first test with no acceleration enrichment, we saw the air fuel ratio drift all the way to 26:1 or something ridiculous. Okay, so we're still a little lean. This time we've gone to 18.0:1, so we're definitely lean, but we're far better than what we had originally. Now this is a good time to discuss what we're actually looking for when we're trying to tune this function. Now, a lot of tuners will think that what we want to achieve is an absolute perfect line that drops from our initial lambda target to whatever the lambda target is at wide open throttle. Now, obviously on the face of it, that seems to make a lot of sense. However, what you also need to understand is there is a latency between the response of our lambda sensor, depending on whereabouts that's fitted in the exhaust. And in general, what we're really trying to achieve is smooth, crisp acceleration from our engine. So there is a trade-off here, and we're using two parameters to decide on the amount of fuel enrichment we're going to add. First of all, we are going to use that feedback from our lambda sensor, but we're not going to take that as 100% gospel. The other input we're going to use is our own feedback of what the car feels like and what the engine sounds like. And this is again in our courses, I describe that often tuning the acceleration enrichment is better done out on the road, and the reason for that is we can feel any hesitation or any problems with the engine crisply accelerating. Often on a chassis dyno, that can be masked a little bit. We don't really have that same feel that we get out on the road. But those are the two things we're using. We're using the feedback from our lambda sensor to know that we're on track, but I'm not going to be beating myself up if I see that air-fuel ratio hit perhaps 16:1 or 15:1 momentarily. If the engine is very crisp and smooth, then I'm going to be happy with that. However, it would seem that in this case our air-fuel ratio is still a little bit lean on that spike. So let's try adding a little bit of additional fuel in here again. And what I'm actually going to do, because probably chances are when I do accelerate the engine, I'm also going to be increasing the engine RPM. Obviously it doesn't stay stationary there simply at 1000 RPM when I hit that throttle. So I've just translated those numbers up further into the higher RPM areas. Okay, so we'll hit the throttle now and we'll see what effect we get now. Okay, so that looks better, and let's just stop our logging, and again we'll have a quick look and see what we've got here. I'll just bring that back over so we can see it. Okay, so this is looking now a bit more like where I'd be happy to see it. We still have a really slight lean spike, and we're sitting up, like the leanest I see there is about 17:1, but it is very, very brief, and I can tell audibly the engine's response is crisp. As I say, that for me is probably more important than the reading from the lambda sensor. We've also dropped, we haven't gone too rich as well, so it's a trade-off between adding enough fuel that we get crisp throttle response without getting a very rich area after the initial hit of the throttle. So that's another area. If you try and chase this little lean spike and get it 100% flat, often what you're going to end up with is, once the initial hit of the throttles happened, this area here, which at the moment is not too bad, is going to end up becoming richer than what we'd like to see. Okay, so let's just try adding a lot more fuel though, so we can see what it looks like when we've gone too far. And well, hopefully this will be too far. And we'll start our PC logging again. Okay, that's absolutely perfect. That's done exactly what I'd hoped for. Right, so let's stop our PC logging and we'll zoom in on one of these acceleration events here so we can see what's happened. Okay, so again, our green line here, we've got a very, very slight lean spike. It's gone to 15.4, and this is what I was talking about, not trying to beat yourself up about chasing a perfect flat line. What you can see there is though we actually end up dipping rich. And this will be just as bad for our throttle response as if we're too lean. So what I'm looking for in the perfect world is a situation where our air-fuel ratio does spike a little lean, just a little bit lean, and then quickly drops back to our target. That's where I'm going to be happy, and I'm going to trade that off the lambda response versus the feel. So that's the important part to understand, is don't try and work everything out based solely on the feedback from your lambda sensor. So what I'm going to do now is we'll just change these numbers around a little bit. I'd just gone too far, so what I'll do is I'll halve these back to about where I was, and we'll just try doing some tuning in steady state on the dyno and show you how we can fill in the rest of this table. Now this is one area I've said to you that in general it's easier to tune the feel side of the acceleration enrichment when we're out on the road, because we do get that feel. But certainly the dyno does make it easy to be very accurate in adjusting the individual zones, because we can use the dyno, as I've done now, to hold a steady state RPM. So what I'll generally do with this is I'll start by tuning the 1000 RPM area. So that's generally where we're at idle, and I'm going to start by tuning there, and we can do that really simply with the engine just sitting there at idle, and then a very fast blip of the throttle like you've just seen me do. However, once we've done that, then we can use the dyno to just move up these zones, and so now I'm operating at the 2000 RPM area, and it's as simple as operating the engine in steady state and then doing exactly the same thing. We'll just give the throttle a wide open blip and see how that responds. So I'll just bring the engine back to a stop while we're looking at that, and we'll zoom in and have a look at the acceleration we have from 2000 RPM. If I can ever get there. Right. Always pays to start by highlighting the right point in your log file. Okay, so again, we've got probably about what I would expect to see. So on paper, you'd think this is too lean. We're seeing a spike to almost 18:1, and I could very well start now by adding a little bit of additional fuel. What we have got is a drop here pretty well straight onto our target of 13:1, and in fact what we do have is a little bit of a lag. So straight after the acceleration event, we're still sitting at about 13.6:1. So that would be enough evidence to me that yes, I probably would go and add some additional fuel enrichment in this point. Now the other thing that I am adding here is, again, in the log file, we've got our throttle rate being logged, as well as the amount of additional fuel through our wall wetting being applied. Now generally, when we've got one of these tables correctly tuned, and obviously for the purposes of this webinar I am being pretty rough and coarse in my adjustments, what we'll generally see, and this is always a good indication that you've got a table tuned correctly, is the numbers will decrease smoothly and consistently as we get higher in the RPM. And you may well find that once we get up perhaps above 5000 RPM, it wouldn't be uncommon to see all or almost all of our acceleration enrichment being reduced to zero. So for the purposes of this test though, let's just go and add a little bit of additional fuel, and we'll see if we can smooth out this lean spike that we've got here, and at the same time get us back onto our target of 13.0:1 a little bit quicker than we currently are. So I'd say we're pretty close, but not quite right. So what I'm going to do is I'm going to just add a little bit of additional fueling enrichment in that 2000 RPM area. And when I'm doing this, you kind of get a feel for how much difference you need to make to these numbers based on the testing we're doing. So all I'm going to do, I've got no magic that tells me that those numbers need to now be 15, 30 and 40. I'm basing my decision simply on the amount of difference in the measured lambda we saw when I made my last changes, so you start to get a bit of a feel for what size of change will have what effect. Alright, let's get our logging back running and we'll see how our second change influences the shape of that curve. When you're doing this as well, it always pays to just let the engine stabilize it at your test RPM for a little bit, just to make sure everything's back at the same condition, so your intake air temperature and your coolant temperature are consistent when you first hit the throttle. Otherwise you may have other factors that are masking your acceleration tuning. Alright, so let's just go to full throttle now and we'll see how that affects us. Okay. Have a look at our logging and see if we are any better there. Okay, so in this case, this is probably a pretty good indication that we've really made no improvement. You can see that our peak air fuel ratio, our lean point, is still sitting at 17.2, but now what you can also see, and this is to do with how long that acceleration enrichment is active for, we drop to our target of, depending on where I click in the log file, 13:1. We're actually gone a little bit rich, and then it actually cycles back a little bit leaner before stabilizing. So really for that change I haven't seen any net improvement, so I'd probably go back, but particularly based on the fact that the response of the engine was crisp, I'd go back to the numbers I previously had. Okay, so that gives you a broad idea of how to approach the tuning, and what we're going to do is step up each of those sites using the steady state tuning on the dyno. Now it's also worth just touching on the fact that in the table we do have the ability to adjust the acceleration enrichment based on how sharply or how quickly the throttle's being opened, and so far I've ignored these smaller areas of our throttle rate of change. So quite often when we're driving the car we may accelerate through a gear or move the throttle to request some acceleration without going anywhere near full throttle. And in this case we still need some additional acceleration enrichment, but this time we probably haven't resulted, because we haven't gone to full throttle very sharply. We haven't seen the same change in manifold pressure that we would have if we've done a full closed throttle to wide open throttle hit instantly. So in that case we're going to end up operating in these smaller rate of change areas, and we can go through the same process and adjust those areas independently of what we've got when we're making very aggressive changes in throttle position. And that's going to allow us to fine-tune the acceleration enrichment dependent on how quickly the throttle's being opened. One more point just to mention before we move on and look at the coolant temperature correction is we also want to make sure that in the area around zero rate of change we don't have any acceleration enrichment happening. This can be very frustrating. It's caught me out a few times in the past, and particularly where you've got an old throttle position sensor or one that perhaps has for some reason a lot of noise on the input. Even when we're running the car in steady state, we may find that the throttle position is jumping around quite erratically. Okay, the fix for that is obviously to rectify the problem with your throttle position sensor or wiring. However, it's important to just keep an eye on this, because if you don't notice what's going on, you can be wondering why it's almost impossible to get consistent air fuel ratios when you're doing the first part of your job, which is tuning the VE table. And that's because you're going to have this acceleration enrichment acting over the top all of the time, because your throttle position's jumping around. So in essence, the ECU thinks that you're going like this on the throttle the whole time, even when clearly you're not. So a good way of checking that is to log. You can see here the orange line in this log is our acceleration enrichment or our wall wetting, how much fuel is being added. So we can always check on that component and see if there's any acceleration enrichment being added. Okay, lastly we'll talk about our wall wetting 2 table and how we go about adjusting that. We will be coming up to some questions and answers, so if you've got anything that's cropped up, now's a great time to ask those in the chat box and I'll address those. So again, what we want to do is start by tuning our complete wall wetting 1 table, getting that completely filled out and getting good crisp throttle response regardless of how aggressively we're opening the throttle and what our RPM is. So that's our first job. Once we've done that, what we can do is then allow the car to cool completely. And what we want to do is basically go through the same process with the engine from a cold start. And particularly down in the probably 0 to 40 degrees centigrade areas of the table, in that area we quite likely are going to need to start adding some additional fuel again. And remember, that's because the port wall is cold and we've got a larger puddle of fuel in our fuel film. So the process is not much different to what we did with tuning the main wall wetting 1 table. All we want to do is log our lambda, also feel the response of the engine, and then make some changes into these areas as we see fit in order to get crisp and smooth throttle response when the engine's stone cold. And this becomes normally more prevalent when the engine is cold. What you'll probably find is, even with the wall wetting 1 table set up correctly, if we mash the throttle straight to the floor when the engine is absolutely stone cold, you'll probably find that the engine may almost stall, or it's almost as if the injectors have been turned off and there's absolutely zero response from the engine before a hesitation, and then finally it catches its breath and picks up. So we can simply add fuel into this wall wetting 2 table until we get the same sort of response that we had when the engine was warm and at operating temperature. So again, these are additive, they work together, so we need to do the wall wetting 1 tuning before we look at wall wetting 2. I said that was the last thing we were going to look at, but I lied, there is one more. We're also just going to briefly talk about deceleration and alignment, and that is handled over here where we've got a negative value to our rate of throttle change. So this is to handle what happens when we step off the throttle very quickly from wide open throttle. Remember, the fuel film works exactly the same, or in the opposite direction. When we go from wide open throttle to closed throttle, the fuel film is going to evaporate and be drawn into the engine, so the engine will tend to run richer momentarily while that fuel film reaches equilibrium again. So we can use these numbers here to help reduce the fueling when we've got a negative rate of change of throttle, so when the throttle is being closed. This, as I said, I briefly touched on this is probably less critical to have absolutely 100% right than the acceleration side of it, and simply because it's going to have no effect on the feel of the engine. At that point we're stepping off the throttle, so we're not really looking for engine performance or engine torque, so we're not going to feel this. At the same time, we'd like to have a reasonably tight control over our air-fuel ratio and make sure that we're not going excessively rich, and that's what we can use to affect that. Okay, we'll move into some questions now. So again, if you do have anything that's cropped up you'd like me to explain more, this is the ideal time to ask them, and we'll have a look and see what we've got here. Okay, so I saw that Janu had asked a question right back at the start, so good to have you in there and enthusiastic about learning more about this. And Janu's question was, when tuning the tip-in on a stock reflash ECU, is it normal that the short-term fuel trims always spike up to 10 and then comes back to like 3%? Look, in my experience, yeah, you will find that is pretty typical. The short-term fuel trim response in a factory ECU is normally very, very quick, and that will be just affected by that slight lean spike that we saw even in the AEM Infinity. So again, it's the important part of this is to go more by the feel of the engine response rather than strictly what you're seeing in the logger. Obviously, the logger and your air-fuel ratio is still important, and it's going to be some important feedback. but I see too many tuners chase their tails and go round in circles trying to achieve a perfect flat line, or what they consider the air-fuel ratio response should be, and ending up with a result that's actually worse to drive than if they'd simply tuned the acceleration enrichment by feel. So that aspect that you're noticing there is simply the closed loop system of the factory ECU, and you're never going to get a situation where that just sits at zero. So I would not be particularly worried about that. Particularly those closed loop short-term fuel trims have the range of plus or minus 25, so you're getting nowhere near there, so I would not be concerned at all. Drew 6 has said, does the puddle effect also apply to carburetted applications? That's actually a really good question, and I'm going to say right up front here, carburetors are definitely not my forte. They're an area that I've just never delved into, and I tend to leave them to the guys who are good at them. However, I could see exactly the same thing if coming into play. Obviously we've got a slightly different situation in the way that the carburetor delivers the fuel into the intake manifold, but sure, absolutely, some of that fuel is always going to condense out on the port wall. There's no way you can really get around that. One aspect with the carburetor that probably even makes that situation worse is the distance that the carburetor is located from the valve compared to a modern port injected fuel injected engine. So yeah, you're definitely going to still suffer from some of that effect. I couldn't tell you which key on the keyboard that you need to press in order to fix your acceleration problems with a carburetor. Perhaps try a hammer and a chisel, I think. Janu's also asked, can the engine suffer severe knock damage from incorrect enrichment setting? Not really. You're not going to result in knock as a case of acceleration enrichment settings being incorrect. Now, some ECUs will have the ability to give you what they call tip-in retard or accel retard, where you can retard the ignition timing in response to a sharp throttle input. Now, again, over my experience of 15 odd years, and I've literally tuned thousands of engines, that situation of an engine suffering from really bad acceleration or tip-in knocking, I can think of two situations. Funnily enough, both of them were Evo circuit cars where that was actually a problem for me. And I can tell you from first-hand experience, because I still remember both of those cars, it was nothing to do with the acceleration enrichment, and in fact, trying to fix that with acceleration enrichment was completely ineffective. So it was the ignition retard event that I needed to deal with, or sorry, tip-in retard that I needed to deal with. So no, you've got nothing to worry about there. Lith said, it's hard to tell with the clip when you gave it a rev with no enrichment. Was there any noticeable hesitation? Actually, it's a really good question that you've asked there, Lith, and no, in this instance there wasn't, and that's probably reasonably unusual. Normally with zero acceleration enrichment, you're going to, particularly from that completely closed throttle idle situation where you hit the throttle, you're going to notice a momentary hesitation. So you'll punch the throttle to the floor and the engine will just die momentarily before coming back to life. That's a really clear indication that your acceleration enrichment is simply wrong. But in this case, there wasn't actually any effect like that. So it makes it a little bit harder for me to describe, although for you guys at the end of the webinar window, probably very difficult for you to tell unless you can really audibly hear that occurring. So actually, I'll just talk about that because that is a good point. So these are the indicators where you've got it wrong. And the problem is they can often feel the same. So with zero acceleration enrichment, that's often what you're going to feel. You're going to feel this big hesitation when you go sharply to full throttle. The problem is if you've got way too much acceleration enrichment in there, you're going to end up with the air-fuel ratio going massively rich on that throttle hit, and you're going to actually end up with exactly the same feeling, a very doughy response. So this is really to go back a little bit. The ideal way, in my opinion, to tune this is to start with minimal or no acceleration enrichment. get a feel for what that looks like in your logger, get a feel for what that actually does to your response when you're driving the car, and then start adding some fuel enrichment. And if you really want to go to extremes, you've got plenty of time on your hands. There's no harm in simply adding fuel continuously until you go too far and you get that doughy response, and you can back it off. So that's going to give you a feel for both ends of the spectrum. Somewhere in between there is that happy medium. Generally, I'm going to be trying to aim for the minimal amount of fuel enrichment that I can offer while still getting crisp throttle response. Janu's asked, can I give an example of how to change the tip-in for a stock ECU reflash with bigger injectors? They usually like to use more injector pulse width with pedal delta. How should I modify them when using E85? Do I need even more tip-in? Okay, this is really a question that probably would be better answered in a reflash specific webinar. I mean, you've essentially answered your own questions, but I can't really show you that here in this particular webinar. So yes, you're going to often need to adjust the tip-in injector pulse width when you do change injector size. To answer your question about E85, in my own experience, if the rest of the fuel table is tuned correctly, and in a standalone, when you're reflashing the stock ECU, that's not quite the same process, but when you've got your injectors scaled correctly and your closed loop fuel trims, your short-term fuel trims are all very close to zero, your acceleration enrichment between pump fuel and E85, I normally don't see a requirement for any additional fueling on E85. So if everything else is dialed in for the E85 tune, I don't normally see any need to adjust the acceleration enrichment or tip-in enrichment. The main area where we struggle with E85, other than getting everything scaled correctly to start with, is in the cranking and cold start enrichment. But yeah, I can't really give you information about that in this particular webinar. You'll be pleased to know that Ben and I have been discussing in depth how we can start approaching some reflash tuning, and we do intend to bring out some course material and some webinar material in the future which will be based around that. So while obviously the concepts are identical regardless of what ECU you are running, I do know that there are some obvious discrepancies in how that's laid out and what you actually need to adjust. 93 said, can too much acceleration enrichment or not enough alignment cause the cylinder wash and wear the rings prematurely? Look, it's not really something that I would be overly concerned about. You're much more likely, if you've got your acceleration enrichment settings way wrong, you're much more likely to end up with problems with the way the car drives rather than problems with actually mechanically damaging the engine. And while, yes, if you run the engine excessively rich for a period of time, you will end up with problems with washing the lubricant off the boards and perhaps resulting in premature wear of the boards, the rings, etc. You've got to also understand that acceleration enrichment is something that's only momentary and we're not using it very frequently. So again, much less of a problem. Okay, we'll leave it at that for today, and hopefully that's given you some more information on tuning the acceleration enrichment. Obviously AEM based, but again, some of this is applicable to a lot of different ECU platforms. Again, if you are enjoying the content that we're bringing to you, you're enjoying these webinars as well as our courses, please give us a review on our Facebook page. It's going to be really helpful to us. Ben and I would really appreciate it, and it's going to give those considering HPA's courses a little bit more insight into what you guys who have already gone through them are actually getting out of them. So that'd be really useful for us. All right, we'll see you next time. And remember, if you do have any other questions that I haven't covered, anything you want to know that crops up, please feel free to ask those in the forum and I'll address them in there. Thanks, guys.